At 6:40 on a Saturday evening, a country began to disappear from the internet. The island nation of Tonga had just been hit by one of the most powerful volcanic explosions ever recorded with modern instruments. A wall of water struck the coast. Ash filled the sky. And somewhere beneath the Pacific, a violent current of rock, mud, and volcanic debris raced down the slope of the seafloor. It found a black cable no wider than your wrist. The cable snapped. Telephone calls failed. Internet connections vanished. Banks, airlines, government offices, newsrooms, and families trying to contact relatives overseas were forced onto a tiny amount of satellite capacity. The cloud had gone down. Except the cloud was still there. The data centers were still running. The satellites were still above the horizon. The phones still had batteries. What had broken was the road between them. An 827-kilometer strand of glass and steel connecting Tonga to Fiji, and from there, to the rest of the world. For more than 5 weeks, reliable international connectivity remained out of reach. We talk about the internet as though it floats. We upload to the cloud. We stream through the air. We imagine messages leaping from phone to satellite, then falling gently into another person's hand. But nearly every international message takes a different route. It leaves your device by radio. It enters a local network. It crosses streets, cities, and countries through fibre. And when it reaches an ocean, it dives. Down a beach trench. Past the continental shelf. Across mountains, canyons, volcanoes, and plains that no human being will ever see. Then up another beach, perhaps thousands of kilometers away. According to the International Telecommunication Union, submarine cables carry more than 99% of international data traffic. Not satellites. Cables. As of 2026, industry maps track hundreds of active and planned systems and well over 1 million kilometers of fiber on the seabed. Together they carry video calls, financial trades, military communications, cloud backups, search results, medical records, and the tiny blue ticks that tell you someone has read your message. The internet is not weightless. It has glass at its center, copper around its heart, steel near the shore, and salt water pressing against it for 25 years. This is the story of the cable beneath the internet. The machine that made distance disappear. And the fragile, physical world hidden underneath the cloud. Open a video from another continent and press play. There is no pause for customs. No ship leaves a harbor. No operator asks which ocean you would prefer. The image simply appears. That ease is so complete that the machinery behind it becomes almost impossible to imagine. So let us slow the first second down. Your phone sends a short radio signal to a nearby router or mobile tower. From there, the request joins a terrestrial fiber network. Routers read its destination and pass it onward, not as one continuous object but as packets, small pieces of information that can take different routes and be reassembled at the other end. If the requested video already sits in a nearby data center, the journey may stay on land. But if it has to cross an ocean, the packet eventually reaches a cable landing station. These stations are often deliberately boring. A fenced building behind a beach, a concrete room near a fishing village, a secure compound beside a road that tourists pass without noticing. Inside are lasers, switches, power feed equipment, and the point where a national network becomes an international one. The light enters a hair-thin strand of glass. Then the internet goes underwater. The popular picture is a single web stretched neatly between continents. Reality is messier. Each cable system has owners, landing rights, maintenance agreements, capacity contracts, and routes chosen around politics as carefully as around underwater mountains. Some systems connect 2 points directly. Others have branches that split toward several countries. Some were financed by groups of telecommunications companies. Increasingly, large cloud and content companies invest directly because their own services consume so much international capacity. But a cable is not the internet. It is one road in a network of roads. Routers at each end decide which road the traffic should use. If one cable fails and enough spare capacity exists elsewhere, users may notice nothing. Their packets are rerouted in milliseconds or minutes. That redundancy is why the world survives the roughly 4 cable faults reported in an average week. It is also why a fault can be invisible in one country and catastrophic in another. London, New York, Tokyo, Singapore, Marseille, and other major hubs have many routes. Small islands may have one. A wealthy market can buy diversity. Different landing beaches, different owners, different oceans. A country with one narrow connection cannot reroute around geography. For Tonga, the cable to Fiji was not just another link. It was the link. That is the first rule of the underwater internet. Resilience is not the strength of one cable. It is the existence of another path. And the second rule is even stranger. For most of its journey through the deep ocean, this infrastructure is surprisingly small. Close to shore, where anchors and fishing gear are dangerous, a cable can be wrapped in heavy steel armor. Far out at sea, beyond the reach of ordinary human activity, it may be little wider than a garden hose. Inside are only a few glass fibers. The international economy is squeezed through strands about as thin as human hair. That sounds like a miracle of the digital age. But the first version was attempted before the American Civil War had ended. In the middle of the 19th century, the Atlantic Ocean was not just distance. It was delay. A message between Europe and North America traveled as fast as the ship carrying it. News, prices, diplomatic instructions, and family letters spent roughly 10 days at sea. The electric telegraph had already changed communication on land. A pulse could travel along a wire and become a mark, a click, or a letter hundreds of kilometers away. The obvious question was also the unreasonable one. Could the wire keep going? Early submarine cables worked because of a material called gutta percha, a natural latex imported from Southeast Asia. It could insulate copper from seawater while remaining flexible enough to be wrapped around a conductor. In 1850, a cable was laid between Britain and France. It did not last. According to an early history published by the ITU, a French fisherman reportedly mistook the strange line for seaweed and cut it apart. The replacement was stronger. Soon, short submarine links began stitching nearby coasts together. But the Atlantic was different. It was deeper than engineers could properly map, wider than any completed cable, and violent enough to turn a controlled experiment into a disaster. The promoter who refused to let the idea die was an American businessman named Cyrus Field. Field was not the inventor of submarine telegraphy. His talent was persuasion. He convinced investors, engineers, scientists, and governments that a cable between Ireland and Newfoundland was not only possible but inevitable. Attempts began in the 1850s. Cables snapped during laying. Expeditions turned back. Money disappeared into the water. Then, in August 1858, signals finally crossed the Atlantic. Queen Victoria and President James Buchanan exchanged formal messages. Cities celebrated.
Bells rang.
Newspapers declared that time and space had been defeated. The victory lasted only weeks. The cable was weak. Its signals were difficult to detect. In an effort to force clearer messages through it, Dangerously high voltages were applied. The insulation failed. The ocean became silent again. For Field, the humiliation was public. Critics had evidence now. The Atlantic cable was not merely difficult. It appeared to be an expensive fantasy. But failure had produced data. A British inquiry examined the design, materials, manufacturing, testing, and electrical methods. Engineers improved quality control. The physicist William Thomson developed sensitive instruments that could detect faint signals without abusing the cable. Then history intervened. The American Civil War delayed the next serious attempt. By the time the project returned, the cable had a ship built on an almost absurd scale. The Great Eastern. Originally designed as a giant passenger liner, the Great Eastern was large enough to carry an entire Atlantic cable in its tanks. The 1865 expedition came painfully close. The cable broke and vanished into deep water. The following year, they tried again. On July 27, 1866, the line reached Newfoundland. Messages that once spent days on a ship could arrive in minutes. Then the Great Eastern went back into the Atlantic, found the cable lost in 1865, pulled it from the ocean, and completed that one too. Two working paths now crossed the sea. The first global information network did not begin with a browser. It began with copper, tree sap, iron wire, seasick engineers, and a businessman who kept asking investors for one more attempt. The cable did more than accelerate messages. It changed what now meant. Markets on opposite shores could react to the same price. Governments could issue instructions during a crisis. Newspapers could print events before they became history. The ocean still existed, but the delay inside it had collapsed. The Victorian cable carried telegraph pulses. One message, one letter at a time. The modern cable carries millions of simultaneous conversations, streams, searches, and machine-to-machine transactions. The difference is not simply that the cable became faster. The thing moving through it changed. For decades, submarine systems used copper conductors for telegraph and later telephone signals. In 1956, TAT-1 became the first transatlantic telephone cable. Could carry 36 simultaneous voice calls. 36. That was a major achievement. Before it, transatlantic telephone service depended mainly on radio and was limited, expensive, and affected by atmospheric conditions. The cable made a live conversation across the Atlantic feel dependable. But copper has limits. Electrical signals weaken, interfere, and require heavy infrastructure to carry more information. Glass offered a stranger solution. Do not send electricity through the data path. Send light. An optical fiber guides light through a central core by exploiting total internal reflection. A laser can switch extremely quickly, encoding information into patterns that equipment at the far end interprets as bits. Even that description is too simple. Modern systems send many colors or wavelengths of light through the same fiber at once. Each wavelength becomes another channel. Coherent receivers examine not only brightness but properties such as phase and polarization, extracting more information from every pulse. In 1988, TAT-8 became the first transatlantic fiber optic cable. Compared with the copper systems before it, capacity began to rise at a pace that made old comparisons ridiculous. Light still fades as it travels through glass. So along a transoceanic cable sit repeaters, sealed pressure-resistant cylinders placed at intervals of roughly tens of kilometers. They do not open your email or read the address on a packet. They amplify the optical signal and send it onward. The repeaters need electricity. That is why a modern fiber cable also contains a copper conductor. Landing stations apply thousands of volts of direct current along the line, powering amplifiers in series across the ocean. At the center is data made of light. Around it is a power system. Around that are layers designed to keep water out and tension under control. In deep water, the cable can be thin because the ocean floor is quiet. It is cold, dark, stable. Sharks have become famous in cable mythology, helped by a few memorable videos and the fact that Shark Attacks Internet is an irresistible headline. But the everyday enemies of submarine cables are far less cinematic. Fishing gear, anchors, human beings doing normal work in the wrong place. That danger is concentrated near coasts, so cable armor changes with depth. Shallow water sections may receive one or more layers of steel wire. In suitable seabed, they are buried. Far offshore, heavy armor becomes unnecessary weight. The cable rests on the seabed, protected mostly by depth and obscurity. This creates one of the internet's best visual tricks. A cross-section of the cable looks huge in a diagram because every layer needs room for a label. In your hand, the deep-sea version can look almost disappointingly ordinary. A black hose. No blinking lights. No visible stream of photographs. No hum of global finance. Yet inside those fibers, light is divided into wavelengths, wavelengths into channels, and channels into more information than the builders of TAT1 could have assigned names to. The achievement is not that one signal crosses an ocean. It is that the cable keeps so many signals separate, strong, synchronized, and recoverable after thousands of kilometers. And before any of that can happen, someone has to build an object longer than a continent and lower it into a place where repairs may take weeks. A submarine cable does not begin on a ship. It begins with a route. Survey vessels cross the proposed path, measuring water depth and mapping the seabed. Engineers look for steep slopes, unstable sediment, volcanic zones, coral, deep canyons, fishing grounds, shipping lanes, existing cables, pipelines, and unexploded weapons. The shortest route is not always the safest. The safest route is not always politically possible. And the route with the best landing point may lead directly through someone else's territorial waters. Permits can involve national regulators, coastal authorities, environmental reviews, port rules, and negotiations with the communities that use the sea. Then manufacturing begins. Fiber is grouped and protected. A copper tube or conductor is added to carry power. Steel strength members take the mechanical load. Polyethylene keeps water out. Extra armor is applied for the dangerous approach to shore. The cable is made in long sections and stored in enormous circular tanks. Workers flake it into coils, carefully placing each turn so kilometers of cable can leave the tank in the correct order without tangling. The geometry is hypnotic. It is also unforgiving. A cable can be designed to survive decades under pressure and still be damaged by one careless bend on deck. Loading a cable ship can take weeks. Repeaters and branching units are inserted at planned positions. Every component is tested. Spare cable, joints, grapnels, buoys, remotely operated vehicles, and repair equipment travel with the system. At sea, the ship follows the survey route with slow precision. In deep water, cable is paid out from the stern and settles through kilometers of ocean. The ship must give it enough slack to follow the terrain, but not so much that loops form. Near shore, a sea plow may be lowered to the seabed. The plow cuts a narrow trench, guides the cable into it, and allows sediment to fall back over the line. In vulnerable areas, burial can reach meters below the seabed. Where the ground is rocky, engineers may use protective covering, articulated pipe, or a different route. The landing itself reverses the scale of the project. After crossing an ocean, the cable has to reach a specific beach. A A smaller vessel or floating line of buoys guides the shore end through shallow water. Crews pull it across wet sand and into a conduit. Divers check the path. The cable disappears into the landing station. Then the beach is restored. Soon people walk above it. Children build sandcastles. Dogs chase waves. Fishing boats leave before sunrise. Underneath them is a border crossing for light. An optical submarine system is commonly designed for a life of around 25 years. But capacity is not fixed for the entire life of the cable. Engineers can upgrade terminal equipment on land. Better transmitters, receivers, coding, and signal processing can push more useful data through fibers that were laid years earlier. This is one reason submarine infrastructure feels both old and new. The wet plant, the cable, repeaters, and branching units beneath the ocean is built to be left alone. The equipment at the ends continues to evolve. The road stays in place. The vehicles become smarter. And then there is the environmental question. Laying and burying cable disturbs the seabed, especially during installation. Route planning matters. Sensitive habitats can be avoided, and post-installation surveys can reveal exposed or poorly buried sections. NOAA's reviews describe the overall environmental effects of telecom cables as generally modest when projects are planned and installed correctly, but not imaginary. Infrastructure does not become harmless merely because it is useful. The deeper truth is more practical. We already depend on this network. The responsible choice is to understand where it lies, how it is installed, and what happens when the ocean refuses to leave it alone. Somewhere in a landing station, a monitor changes. Light is no longer returning as expected. Traffic begins moving to other routes. Engineers need to answer 3 questions. Which cable failed? Where? And is there a ship available to reach it? The location can be estimated from shore using optical test equipment. A pulse is sent into the fibre. Tiny reflections return from along the line. A break produces a recognizable change, and the travel time helps calculate the distance to the fault. That gives engineers a point on a route, not a cable conveniently waiting on the surface. The ship still has to find it. In shallower water, remotely operated vehicles can inspect the seabed. In other conditions, a ship may drag a carefully chosen grapnel across the route until it catches the cable. The line is cut if necessary. One end is lifted. The damaged section is removed. A good end is tested, sealed, and attached to a buoy while the ship retrieves the other side. New cable is spliced between them. The repaired line is tested again, lowered, and sometimes reburied. This sounds neat when reduced to verbs. Locate, grapple, lift, splice, test, lower. At sea, each verb can become a day. Weather stops work. Water depth changes the amount of cable and tension involved. Permits delay entry. Customs rules delay equipment. A suitable repair vessel may be serving another fault thousands of kilometers away. ITU design guidance estimates that a marine repair can take roughly 1 to 3 weeks depending on location, depth, vessel availability, cause, and weather. For a well-connected region, that can be an inconvenience hidden by rerouting. For a single cable country, it can be isolation. More than 170 cable repairs were reported worldwide in 2025, almost 4 per week. The number sounds frightening until you compare it with the size of the network. Hundreds of systems. More than 1 million kilometers. Decades of service. Breaks are routine because the network is enormous. Disaster is not the existence of faults. Disaster is a fault where no alternative exists. The majority are not caused by spies. Recent ITU summaries say more than 80% are linked to fishing and anchoring. A trawl door can hook a cable. A ship waiting outside a port can drag an anchor during bad weather. Charts can be ignored. Burial can erode. A line installed safely years earlier can become exposed. Natural hazards account for a smaller share, but they can damage several systems at once. Earthquakes trigger underwater landslides. Storms move sediment. Volcanic eruptions send high-speed density currents through submarine canyons. The 2022 Tonga eruption did not politely break one point beside a repair dock. It damaged the international link and sections of the domestic network in extreme underwater terrain. The repair ship had to wait for conditions, travel to the region, and carry enough replacement cable. Repair crews occupy a strange position in modern life. Their work supports activities measured in terabits, but the decisive moment may involve a human hand guiding a wet black cable over a steel wheel. They maintain the future with methods recognizable to the Victorians. Ships, rope, grapnels, careful joints. The instruments changed. The fiber changed. The scale changed. The ocean did not. Look at a global cable map and the first impression is abundance. Lines cross the Atlantic in bundles. The Pacific is webbed with long arcs. Routes wrap around Africa, connect island chains, and crowd into Southeast Asia. But abundance is not the same as diversity. Many lines converge. Geography creates funnels. Europe and Asia are separated not only by distance but by land, borders, and narrow seas. A large share of traffic between them passes through the Mediterranean, Egypt, the Red Sea, and onward through the Indian Ocean. At the Strait of Malacca and around Singapore, dense networks meet one of the world's busiest shipping regions. Across the Pacific, routes concentrate near major landing hubs in Japan, Guam, Hawaii, the Philippines, and the west coast of North America. On the Atlantic edge of Europe, places such as Cornwall, Ireland, France, Spain, and Portugal host beaches that happen to sit near data centers, power, and onward fiber routes. A landing point is valuable because other cables already land there. That success can create concentration. The physical path is only part of the choke point. Traffic also depends on terrestrial fiber between landing stations and data centers. It depends on power. It depends on permits, repair ships, and the ability to cross a country between two seas. Egypt is the clearest example. Its geography offers one of the shortest practical paths between European and Asian networks. Cables land on the Mediterranean, cross Egypt by terrestrial routes, and re-enter the water toward the Red Sea. The route is efficient. It is also difficult to replace. Cable maps can mislead in another way. The lines appear precise, as if anyone with a screenshot could sail to a fiber and lift it. Public maps are usually schematic. Exact routes may be simplified, and deep ocean position alone does not make a cable easy to reach. At several kilometers depth, finding and manipulating a narrow line is specialized work. Near shore, however, the risk changes. Cables are shallower. Shipping is denser. Routes are better known because mariners must avoid them. Protection is a balance between secrecy, safety, and maintenance. The real defense is not hiding every cable. It is building a network that can lose one. Separate landing beaches. Routes that do not share the same canyon. Spare capacity on other systems. Repair agreements made before a fault. Countries with multiple paths can absorb damage that would disconnect an island with one path. This is why a beautiful global map should be read twice. First, notice how connected the world has become. Then look for the places where all the lines squeeze together. In March 2024, damage to several systems off West Africa disrupted connectivity in multiple countries. Evidence pointed to a subsea landslide in a region where routes share geography. The lesson was not that cables are badly designed. It was that independent-looking lines on a screen can experience the same physical event. Two cables are not redundant if one landslide can cut both. Two landing stations are not independent if they share the same terrestrial corridor. Two providers are not protection if they lease capacity on the same wet plant. Resilience lives in details the map does not show. The early Atlantic cables were national projects, private gambles, and international agreements mixed together. Modern systems are no less complicated. A cable may be owned by a consortium of telecom operators. Capacity can be divided among investors. Other companies lease wavelengths or buy long-term rights to use part of the system. Then the largest users of international bandwidth began building roads of their own. Search, cloud computing, social media, video, software updates, and artificial intelligence move extraordinary amounts of data between private data centers. Telegeography's industry research found that content and cloud networks accounted for almost 3/4 of international bandwidth demand in 2024. That is demand, not 3/4 of every cable. The distinction matters. But the direction is clear. Companies such as Google, Meta, Microsoft, and Amazon are no longer merely customers of the submarine cable industry. They invest in systems, join consortia, and in some cases build private cables designed around their own data center routes. This can bring new capacity and more paths. Can also shift power. The infrastructure beneath international communication was once dominated by telephone carriers and governments. Increasingly, a small number of technology companies influence where new capacity is built, which data center regions connect directly, and which markets become hubs. That does not mean a company can simply own the ocean. Landing permits, environmental rules, maritime law, telecom regulation, and partnerships still shape every route. But the cable map is also a map of investment priorities. Some places receive several new high-capacity systems. Others wait for one affordable connection. The geopolitical questions are older than fiber. In war, cables carry military and diplomatic traffic. In peace, they carry financial and governmental data. States worry about interception, espionage, coercion, and sabotage. During the First World War, Britain cut German telegraph cables. During the Cold War, intelligence operations targeted undersea communications. Today, the tools include submarines, remotely operated vehicles, cyber access to landing stations, and, most simply, anchors. But suspicion is not proof. In late 2024, several communication and power cables in the Baltic Sea were damaged in separate incidents. Investigations examined vessels and anchor dragging. NATO increased its presence and described some incidents as under scrutiny for possible sabotage. That careful language matters. An anchor can be dragged deliberately. It can also be dragged through negligence, bad weather, mechanical failure, or poor seamanship. The physical evidence may show how a cable was damaged without proving why. The documentary version is tempting. A dark ship, a secret order, a line cut in the night. The responsible version leaves room for uncertainty. Governments are responding anyway. NATO created new coordination and monitoring efforts for critical undersea infrastructure. The European Union adopted a Cable Security Action Plan in 2025 covering prevention, detection, response, repair, and deterrence, including work towards stronger repair capacity. The ITU and International Cable Protection Committee created an international advisory body focused on cable resilience. This is not evidence that every fault is an attack. It is recognition that the consequences are strategic even when the cause is ordinary. The same infrastructure can be vulnerable without being defenseless. Its strongest protection remains visibility at sea, cooperation across borders, rapid repair, and enough alternate routes that breaking one line does not break a society. The demand curve keeps rising. More video, more cloud services, more data center replication, more machines exchanging information without waiting for a human to press send. The answer is not one infinitely powerful cable. It is better use of glass and more routes. Older systems often used a smaller number of fiber pairs, pushing each pair toward higher optical power and complexity. Newer designs increasingly use spatial division multiplexing, more fiber pairs, each operated at efficient power levels. The 2-Africa system, completed in its core form in 2025, uses up to 16 fiber pairs in parts of the network and circles much of the African continent, with branches to Europe and the Middle East. The scale is impressive. The more important idea is architectural. Capacity, landing diversity, branching flexibility, burial depth, and route selection are designed together. Future resilience will look less like an indestructible cable and more like a network expecting damage. New paths can avoid known hazard zones. More countries can connect through multiple neighbors. Cable corridors can be monitored alongside ship movements. Repair permits can be prepared before an emergency rather than negotiated while a nation is offline. Spare equipment and vessel agreements can be positioned regionally. And traffic can be engineered so backup capacity is actually available when everyone needs it at once. What about satellites? Low Earth orbit constellations have changed the answer, especially for remote places. They can deliver useful broadband where terrestrial and submarine infrastructure is absent, and they can provide emergency connectivity after a disaster. For an island with one cable, that backup can be transformative. But satellite and submarine systems solve different parts of the problem. Satellites offer reach, mobility, and rapid deployment. Fiber offers immense bulk capacity, energy efficiency, and direct connections between the data centers where so much traffic begins and ends. The future is not cable or satellite. It is cable and satellite, each covering the other's weakness. There are also experiments that treat fiber as more than a communication path. Researchers can examine changes in light traveling through a cable to detect vibration, temperature, and seismic activity. Under the right conditions, existing fiber may help observe earthquakes, ocean waves, or movement on the seabed. The idea is still developing, and not every commercial system can become a scientific instrument. But it offers a poetic reversal. For most of history, the ocean made communication difficult because we could not see through it. Now the communication line itself may help us see the ocean. The challenge is that new capacity can reproduce old inequality. A cable landing does not automatically make internet service affordable. The benefits depend on competition, national backhaul, local data centers, reliable electricity, regulation, and the price charged to households. A fiber at the beach is potential. Turning it into access is a political and economic project on land. That is why the story cannot end with a glowing line on a map. The map tells us where connection is possible. People and institutions decide who can use it. Return to the beach. The trench has been filled. The workers have gone. The landing station sits behind a fence, quiet enough to be mistaken for storage. Under the sand, a black cable enters the sea. It does not look like the internet. Perhaps nothing could. The internet is too many things at once. A family call from No Ku Alofa. A market opening in London. A doctor reading a scan from another country. A teenager watching a video made yesterday on the other side of the world. A data center copying information so a failure does not become a loss. All of it becomes light. And the light goes down. The first Atlantic cable reduced a 10-day voyage to minutes. The modern fiber network reduces the same distance to a fraction of a second. That speed feels natural only because generations of engineers, sailors, factory workers, divers, regulators, scientists, and repair crews made the impossible routine. They surveyed the floor. They insulated copper with tree sap. They lost cables in storms. They invented instruments sensitive enough to hear a faint pulse. They learned to trap light inside glass. They built ships that can find a line in kilometers of dark water and lift it back into the weather. The result is resilient, but not invulnerable. It survives ordinary faults because traffic can move. It fails dramatically where geography, poverty, or politics leave only one path. It creates connection and therefore dependence. It concentrates power while spreading capacity. It makes the world feel less physical by becoming one of the largest physical systems humanity has ever built. When Tonga's cable broke, the event exposed more than a damaged fiber. It exposed the metaphor. The cloud was never floating above us. It was data centers on land, landing stations at the coast, and glass resting in darkness. The internet did not disappear into the air. It entered the ocean. Somewhere tonight, a pulse of light will leave a building near a beach. It will cross a continent's edge, pass through amplifiers sealed against crushing pressure, slide over mountains no map in your house has named, and climb toward another shore. You will not hear it arrive. You will see a face, price, a sentence, a small blue tick, and for one more moment, distance will disappear. The internet is underwater, and the world is connected by a thread.